Okay, so it's very nice to be here and to see everybody in person. And since I think I'm the only Bayesian talk, so I'll give a little bit of a context of what this whole thing is about. So the talk will be in different pieces. So first I'll talk a little bit about what it is and why we do this. Then some problems we face in the heavy ion collisions and what we've done recently and where we're heading in the future for this. So let's start with the first one. And the underlying goal really is to better understand heavy ion collisions. And in order to understand this, of course, we look at data. And roughly, there are two sets of ways we can operate. First one is what I call the silver bullet measurement. We measure something, we look at it, and we learn something from it directly. So for example, the dihedral correlation, where we see the opposite side is completely gone, and we gain insight directly from that. But this kind of measurement is rarer. We keep having them, but it's relatively rare, especially when we have more and more precise data and more sophisticated models. In which case, we inevitably have to bring in the other side of the equation, which is the model side. So by doing a very rigorous model and data comparison, we can extract the physics we want from it. And this is essentially the goal of the Bayesian analysis. We want to do this in a well-controlled way. Okay, and if we look at how we can compare that data to model, no matter what formalism you use, there's one key question that we inevitably have to face, which is we have to quantify some sort of distance measure between the point in the model space with data. So in this cartoon here, this sheet here is the model space. Each point is one parameter. And we have the truth, which is the data is a proxy of the truth. And we have this distance measure going from the model space to the truth. And if we can successfully write down this distance function, then we're 90% of our way there, because then we can just have fun because all the information is encoded in this function, and it's a function we can analyze. Like we can put in the minimizer, find out where what the fit is, or we can visualize it and whatever. There's a lot we can do. And one of the candidates to do this distance measure is in the Bayesian formalism. So up here, the formula, this is the Bayes rule that many people know. And in here, let's focus on this object called the posterior function on the left-hand side of the equation. And this posterior function essentially is a probability density of some given parameter being the best fit given what we observe in data. So the larger this is, it means that that parameter fits the data better. And if it's smaller, then if it's worse. And essentially, this is a very good candidate to build this distance measure. So we can like take a look and put a negative sign on it in front of it and so on. Okay, so this is the very high level walkthrough of what the key part of the Bayesian analysis. And now let's move on to what's the problems we're trying to solve in heavy ion collisions. Okay, so in heavy ion collisions, things are complicated. And I see there are two main things that we have to get past if we want to successfully understand things from this. So one of them is that in heavy ion modeling, there are a lot of blocks of different pieces. So for example, we have the inertial states, we have hard process, we have the hydrodynamic evolution, and so on and so forth. This is an incomplete list. We can write down a lot of things. And in each of these blocks, there are parameters that we have to specify and learn eventually. And also in the interface between the blocks, there are also parameters, like when do you start the hydroevolution and when do you do the hydrogenization and so on. And essentially, this is a very high dimensional problem that we have to tackle somehow and make it computationally traceable. The other byproduct of this is that each piece is usually written by different experts, and their code does each piece very, very well. But that also means that it's in a very different code system. And if there's just one person want to do the whole thing, that's complicated and it requires a lot of effort. And so for this second problem of the code, this is where JETSCAPE comes in. So as is discussed many times already, the JETSCAPE is a framework that provides a modular design, and it provides the interface for different pieces to fit together nicely. And so now that we have this framework, it's much easier for a small number of people to run the whole thing without having to worry too much about dealing with the specifics of different code. Okay, and the other question for the large parameter space, I would just, so the problem really is computational, because there's a large parameter space and it's also continuous, and it's very computationally intensive to get any predictions from each single point. It's hours to days. And the solution people usually adapt in these kind of analysis is to do interpolation, essentially. So we pick some points, we evaluate to high precision, and we interpolate. And this will give us something that's still high computing cost, but it's at least doable. Okay, and oops. Yep. So there are also a lot of details about the Bayesian analysis that I will not go into the detail for now, because it can easily be a 1-hour seminar. And I would just say that a lot of care goes into making sure each step is robust, and that the analysis itself is robust, both inside the JETSCAPE and also many other colleagues doing similar analysis. Okay, so let me move to what has been done recently in the context of JETSCAPE. So I will not talk about, for example, trajectum and other efforts, but mostly focusing on what's done in the JETSCAPE. So there are two main analyses in recent years. So first one is what we call the soft Bayesian analysis. So the idea is we take the soft observables, the dn d eta, dt, d eta, and so on, and vn, and we try to learn the parameters in the initial state in hydrodynamics and so on. And the model setup essentially can be summarized here. We have a Trento initial state. There are some parameters number of parameters written here that's embedded in there. And then it's free streaming until the hydrodynamic starts. And then we parameterize the viscosities in the kind of empirical way. And then we also explore different models for particularization. And then finally, there's the afterburner for the hadron phase. And once we run through the analysis, we can see that the result. So on the left is what the best fit model compared to the data points. And we can see that there is a decent agreement to both LHC and RIC data, which is very nice to see. And we also get the full correlation between all the parameters used in the analysis. And because this is a JET workshop, I will not talk too much about this, the soft Bayesian part, except I will highlight two things. One is, for example, on the left is the extracted viscosity for both using LHC data only versus LHC plus RIC. And we can see that they are visually different. And this tells us that there's a complementarity between LHC and RIC data, and we can learn something different from different data sets. And I think it's a nice demonstration. And another thing is that there are also some freedom in choosing the particularization model. For example, on the right, this is the viscosity for different underlying model assumptions, and they are very different. So we can see that that piece is very important to our understanding and description of the system. And there are also many other results that I don't have time to go into. But instead, I will focus a little bit more on what we call the hard Bayesian analysis, where we try to extract Q hat. Okay, so the start of this is the analysis done by the JET collaboration. The publication is like 8 years ago. So what they did is that they take the hadron RA data, and then they do a separate analysis to RIC and LHC energies. And they do this for a variety of different models. And the result is summarized on the right-hand side here. So you can see that for different model, they are the extracted Q hat. And on here, you can see there's a step-like structure for all the models. And this is basically because we extract the RIC and LHC and we stitch them together. And the question we will want to ask is that, can we take one step further and use a single unified Q hat description for both of them? Okay, and so that's the starting point of this analysis. So for the analysis setup, we use the 2+1 dihydro, and then we explore different energy loss models. And for the Q hat, we try to use a single function to describe everything. Okay, and the parameterization of Q hat is written like this. So there are two terms in there. One term is the matter-inspired term. So this is more closer to what we would expect if it's in a matter model. And on the second part is the LBT-inspired term. So it's more similar to what we would see in LBT. And we try to parameterize the whole thing using this. So here is an example of the Bayesian analysis process. So before we look at data, you can see the model prediction is all over the place. This is the whole phase space that we explore. And then after we look at data, we can see that there's a huge constraint in power and things converge nicely to where data is, which means that the things is at least working self-consistently. Okay, and then we can also look at the extracted parameter using matter as the energy loss or using LBT as the energy loss. So what's plotted here, the red curve and the scatter plots are what we get if we use the LBT as the energy loss model. And the blue one is if we use the matter as the energy loss model. And we can, for example, see the prefactor A and C here and see how they compare. And in the red one here, where we use the LBT as the energy loss model, we can see that it prefers much more the C term over A term. Whereas if we use the matter, then it prefers much more the A term over the C term, which is a nice confirmation. And we can also see that the B and D terms, the higher order terms, are only very loosely constrained. So with the current data set, we cannot say much about those. Okay, and we can also look at the extracted Q hat as a function of temperature and momentum. So what's plotted here, these are the results from the JET collaboration. And you can see the two bins, which correspond to RIC and LHC analysis. And the result is shown in this band for different energy loss models. We can see that it's compatible with the JET collaboration result. And another thing that I think is pretty nice is that in the inset here, there's the prior range, which is the full range that we explored for the model learning. And this range is much wider than what we extracted in the end, meaning that it's the result here is really detected by the model and not by the range that we put in. Okay. And we also have a multi-stage approach result where we use the matter energy loss for the high virtuality and LBT for the low virtuality. And we have a switching point in virtuality where we switch from one energy loss to another. And this is the result. And you can see that we can extract the best switching virtuality is about 2 GeV. And this demonstrates that there is some value in the two-stage approach because the data is constrained to something. And what's shown here is also the difference between what we get from RIG plus LHC data together in red, and also LHC data only in blue. And here, in contrast with the soft one, we can see that things are very similar between RIG and LHC. And this has a simple explanation. In our case, it's mainly because of the kinematic range we use to feed into the analysis. So in this first iteration, we only use the higher energy points, and there's not much for RIG there. And that's the main reason here. But in future analysis, we can try to expand it, and we should start to see some difference. Okay, so finally, let me have some remarks on the recent results. So first of all, due to the time constraint, many things are not covered. And another thing is that what is done so far is really just the beginning. And there are further analysis and efforts ongoing to expand on this, for example, to more observables and to more flexible models and so on. So yeah, stay tuned. Spend the last several minutes on what we can do with the Bayesian analysis once we have the Bayesian analysis, looking a bit into the future. So this can be classified into different types. So we can improve on the data side, and we can improve on the model side, or about the analysis itself. So on the data side, there are many things that we can talk about. But first, I'll talk a little bit about the choice of data and the scope of data. So I think for most of the early analysis, we only pick a subset of the eligible data. So for example, in the Q-hat analysis, in the first iteration, we only have some of the bins and some of the experiments results, and not everything. And I think this is a point that we have to keep in mind when we go forward, which is that we really need to include all the data that's within the scope. So for example, if we want to look at the jet cross-section, then we should include everything, including the Alice result of RA ratio, and also the RCP from Atlas, even though there's apparently some tension between them. And if we only use a subset of them, then we will get bias. And another thing is about the data scope. And I think the way to move forward is that we should systematically expand the scope of the analysis to probe more and more physics. So we start with something that's the simplest. For example, here, the hadron RA, we only have the single hard particle. And then next step could be, there are many different pathways that we can take. For example, we can add the jet RA, where we'll also be sensitive to particles in the vicinity. And then, for example, jet shape, where we can look at the shape of the softer parts, and so on, so forth. And at the same time as the increase in the scope of data, we should also increase the model complexity to encompass more and more the physics into the modeling part of it. Okay, then let me talk a little bit about the uncertainty treatment, which will become increasingly important as we go on. So the uncertainty for data is becoming more and more important. And for example, here, if you have two data points here with the error bar, and you have the prediction here, then the agreement between prediction and data depends very much on the correlation between the data points. So if they are fully correlated, then this is a 1 sigma effect. Everything moves up and down together. If it's not correlated, it's 2 sigma effect. And if it's anti-correlated, it will be larger than 2 sigma. And this can even be an observation like 5 sigma if it's enough anti-correlated. And so in our analysis, to capture the correlation as faithfully as possible is a very crucial piece of the analysis. And this will be more and more important as time goes on, and the precision will keep increasing. And if we look at one example from the experiments, for example, this is a nice measurement from CMS. we can see that, first of all, there are some global uncertainty factors out, the TA luminosity. And then there are two big categories of the uncertainty. One is the systematic uncertainty, which is everything else. And then there's the statistical uncertainty. And while this is nice to look at, there are some information that's missing on these in order to have the full picture. First of all is that there's no correlation information on the systematic uncertainties. And also on the statistical uncertainty, if you do unfolding, then they will be correlated to some extent. And I think it will be important for the experiments to convey more information about how correlated things are. Maybe not the full correlation matrix, that's a lot of work, but the more information, the better. And that will be very beneficial to move forward, especially the uncertainty size is shrinking. Okay, so let's move to the model. And I will say a few words about the generators. So if we take a step back, what Bayesian analysis does is really defines the region of phase space in the model that matches the best the data, right? And if the generator does not have the required physics, then it's very easy to misinterpret the result. So if you use a very bad model, you will still get something, and that will not mean anything. And I think this is a case for a better vacuum shower modeling. And I'm very happy to see that there are a lot of progress in this workshop. And the ratios, for example, the RAA, RCP, and so on, they help, but not everything is multiplicative. So we will still have some residual effects, even if we look at ratios. Okay, so finally, I will talk a little bit about the analysis itself. There's the question of the computational challenge that I will not go too much into, but I will focus on the extensions. So if we have the Bayesian analysis done, what can we do with it? And I think this is the exciting part. So there are a lot of possibilities that we can do once we have the Bayesian analysis. So for example, if we have multiple models that try to capture the same physics, we can do model selection to see which one is favored by data compared to others. We can also do model combination, which I'll have a slide in a couple of slides. And we can also do a optimal event generation with a full posterior and not just single parameter. Because if you have two parameter points in the model space that does equally well, then we should not pick one or another to generate events, but we should generate with equal proportions. And event generation with full posterior will capture this whole knowledge about data. And we can also do tension quantification. So we can quantify how much tension there is between the different experiment data. And that would be also very interesting application. And this is only a very short list. And there are a lot of possibilities of using Bayesian analysis as a tool to understand different things. So about tension quantification. So the Bayesian posterior essentially is data to model compatibility. And if we have the same model space, if we think that we captured most of the physics in it, and we have different set of experiment data, then we can run the Bayesian analysis on different input data, and then see what's the quote unquote projection onto the model space look like. So if it's on the top cartoon here, then the two sets are not very far apart. And if it's the bottom here, then there are some clear tension in the context of this model. And I think that what's very cool is that it gives us a control way to study compatibility, even if the data bins do not line up, or even if we have different types of data. So for example, there's the high PTB2 and the RPA puzzle. And this is one potential application for that. If we have a model space that we think captures most physics that we want, then we can run this and quantify the tension between different types of data sets. And the last thing I will talk about is the model averaging. So suppose we have different models. They all try to describe the same physics. And they fit the data to a very different degree. And in the Bayesian framework, essentially this is a way to optimally combine the models based on their compatibility with data. And so here is one example that they did in the soft Bayesian analysis. So we have the different particularization models, and we can see that over all of these models, collectively, what do they say about the extracted viscosity? And what's nice about it is that it's complete data driven. So we don't have to put in additional things. This is informed by data, which is very nice. Okay, so let me conclude. My time is up. So the Bayesian analysis is a rigorous way of doing data model comparison. And in this formalism, the Bayesian posterior is the distance function, so to speak, between data and model points. And for the heavy-on problems, usually there are two different problems. One is the different code base, which is partly alleviated by the JETSCAPE framework. There's also the large parameter space where we have ways to deal with it. And for recent analysis from JETSCAPE, there's the soft sector Bayesian analysis, which we learn about both properties, and the hard sector, we extract a Q hat as a first step beyond the JET collaboration. And for the future, we have to think about better data handling and also better models. And there are also a lot of extension that's possible once we have the data Bayesian analysis ready. And I'll be happy to talk more afterwards if people are interested. So with this, I would like to thank everybody and conclude.
We have time for questions.
Yeah, so thanks, Yi, for the very nice talk. So I had 2 points. So first, it would be really nice to see what the impact of the S-Phoenix data would be on the extraction, because, I mean, obviously that should have much more precision than the existing RIC data. Yeah. The second thing is, so you showed the Atlas and the Alice R-scan results as, you know, you wanted to include them even though they were in tension. And I totally agree with that, but there's also another difference between those, is one is published and one is preliminary. Mm-hmm. So I was wondering if that's something that JETSCAPE has thought about how to include, because I know there's a different level of collaboration vetting between those, and also, at least in Atlas, there's a different level of information we provide to the community for preliminary and published results. And I wondered if, well, I know you will publish it. I'm just wondering in general. I mean, that was the example that was shown.
Yeah.
So I was just wondering in general if there was thought in JETSCAPE about how to include preliminary results or whether to.
So I think we should take everything that's available, and regarding preliminary or not, that we have to think more about. But the idea is take whatever is available, anything, without doing any pre-selection.
Yeah, and just to follow up to your comment of using this tool to project the impact of future data. This is used commonly in cosmology, neutrino physics. What's the impact of the next ton scale, neutrino double beta decay experiment, and absolutely S-Phoenix. What will the impact be of S-Phoenix in any of these the calculations? And the question is, well, who's doing that, right? Is this JETSCAPE's business? Is this S-Phoenix business? I'm not trying to farm things out, but I think it's a very broad question. You know, JETSCAPE, you know, that's public domain software, and maybe the field should evolve such that collaborations take this tool to evaluate for themselves what the impact is of future measurements. It's not just, it can also be running strategy. What precision do we have to achieve beyond which it doesn't really get us where we need to go, or what's the minimum precision? So I think that's a very general question of, you know, how this tool is used. JETSCAPE is using it for particular purposes. We have finite capacity. It's a question whether as Phoenix might want to take it over as well for your own specific collaboration purposes.
Yeah, I would say for this exact question, I've been talking with Dennis, and it's on our to-do list, but we're just too busy.
Hi, yeah, this was a great talk. So I wanted to ask you, maybe it's in your outlook or the future thing. So if you have several models, like for instance, those particularization models that overlap in the posteriors, I mean, so what was your idea to try to single out which one is the better? I mean, we were just discussing this week that most of the models, for instance, have this kind of bias effect, already built into them. I mean, energy is lost, so there's always this thing.
Mm-hmm.
So how can you go kind of beyond, right? The model, yeah. How can you distinguish models which give you very similar results? Let's say.
Yeah, well, that's the model selection part that I didn't really talk about. So there's we can use the overall compatibility between model and data point. So the whole space, how compatible it is in layman terms. And then this we can say that which model is more preferred by data compared to others. It's still relative. We cannot get to the 0 point, but we can at least compare between them to see which one is slightly better.
So what's the tool then? Is this called model selection? Is this called model selection, or is there like a test you do, and statistical test, or what?
Yeah, we form a test statistics using the Bayesian, the Bayesian evidence, the denominator in that thing. Yeah, the evidence. Yeah.
Hi, thanks for a very nice talk. I have maybe more of a comment, but also have a question. So you emphasized a bit systematic uncertainties and correlations between uncertainties on the experimental data. Mm-hmm. I recently saw a talk by Wilke van der Schee from Trajectum, who found that there's also a theory correlation uncertainty, and he realized it because now the weight of different experimental inputs is kind of driven by the number of points that we provide from the experimental side. And he realized that for, if you sometimes this pulls very strongly on the model, well, so my question is, have you thought about this? Have you discussed this in JETSCAPE? There's probably no general solution, but what are your thoughts on it?
By correlation, do you mean the input or the output?
So yeah, you can have like two measurements that are sensitive to the same physics, mm-hmm. But maybe one is 1 data point and one is 10 data points. Mm-hmm. And then when you do the Bayesian fit, the inference, the 10 data points will win over the 1 normally. Mm-hmm. Well, maybe from a theory, you think that the 1 data point is more theoretically robust than the 10 data point measurement. And then, so his solution was to put kind of ad hoc weights for different observables to even it out.
Yeah, I think personally, I would tend to just put them on equal footing and let the uncertainty do the weighting, because as soon as we start to put in something that prefers one or another, then we can easily get bias. Yeah, it's the less extreme way of choosing data. Right? It's 100%, 0%, and it's choosing one of them.
So this means that experimental is to bring the data as fine as possible.
Well, if you bin finely, then the uncertainty is also huge. Then overall constraining power shouldn't change that much.
But if it's systematically constrained, any other comments? If not,
actually, maybe just to build on this comment. I mean, I think part of his point, this talk, I guess it was during the Alice week, was that I think it was also saying about how much they really believe the experimental uncertainties and how they correlate with each other, which I think then loops back to Yi's point about if we have better reporting of the correlations between these uncertainties, I think it's a little bit more possible to kind of understand how these different how reliable these different observables might be and how much they're correlated. But I think right for a lot of these, I mean, a lot of these they're kind of just estimating. So we're yeah, the additional information I think can really help us actually make these decisions better than just having to yeah, trying to kind of reweight them. I guess that was more of a comment.
Yeah, actually, so you mentioned you are not asking the experimentalists to provide full correlation metrics, but I thought that should be the ultimate goal. So I got a bit confused. What do you mean by more information?
Yeah, so yes, eventually I think it will be nice if we can all provide full covariance matrix, but given the state of number of people working on experiments, I think that it will delay the analysis by quite a bit for all of them. So what I think instead is that we should release as much information as possible, with the final goal, of course, to get the full covariance matrix. But if not, then, for example, how correlated are the neighboring points? Some indication of that will already be helpful.
No other questions, and let's thank the speaker again.